Good morning, folks. Well, I guess it is evening for me, even though I just finished watching the Sens lose this evening. Very disappointing. But today we're talking about sequences and series, which is very exciting. So, sequences, think of like things going in a sequence, like one and then two and then three and then four. Recursive formulas are kind of like a backwards thinking. So, today we're talking about the definition of a sequence. It's a set of numbers, and it's usually separated by commas and things like that. So, for example, we could see like 1, 2, 3, 4, 5, comma dot dot dot, continuing on forever. You could also see something like 2, 4, 6, 8, continuing on forever, dot dot dot. It even gets a little more complex when you have a series like 1, 1, 2, 3, 5, 8, 1. So 13. We'll talk about this sequence a little bit later on because it's a little bit different. We can kind of see the patterns in the first two, where we're adding one each time or we're adding two each time. But we also see something called a term. Now, a term is something you probably haven't seen before. It's a single value in a sequence. So we write this as T subscript n, meaning the term n. So this could be a 1, it could be a 2, it could be a 3, whatever the first, second, third, or fourth, or a millionth term is. Using the sequence, state T1. So this means term 1. What is the term in the sequence? Well, T1 is 5. So I can see that's the first term that I would see in the sequence. But sometimes we see something called an explicit formula. This is an example of how we represent a term sequence in terms of any different type of function. So for example, I could see something as Tn, which is our explicit formula term, where we have 5 plus 2 and minus 1. All this means is that this is a formula that will give us the terms 5, 7, 9, 11, or whatever the term may be, in terms of a general formula. So think of this as like the y equals mx plus b will give us any point on the line if we plug in an x. The same thing here will give us any point in a series if we plug in a number for n, being the first term, second term, or third term. So this n number is the term number that we are concerned with. So here's an example here. If I'm given the explicit formula below, write the first 3 terms. Okay, so this is the general formula. To get term 1, I just plug in a 1 where I see n. 3 minus 2 equals 1. So term 1 is 1. Easy enough. I do term 2, and I get 4, and I can determine term 3 to be 7. So in order to get my overall term sequence, I would have 1, 4, 7, and continuing on. So this is my term sequence. If I look at this formula here, first 3 terms, the same thing. I'll go back to pink. Term 1 is 1 squared plus 1, which we can see is 2. 2 squared plus 1, so 4, that's 5. And term 3 is equal to 3 squared plus 1, which is equal to 10. So I can see I have this term sequence as being 2, 5, comma, 10, and continuing on. So that's not the hardest part of this. We're talking about sequence and series. How do numbers kind of evolve based on these equations? So think of equations of lines, but we're talking about a series of numbers in this case. We also see something called function notation. Okay, so this is a little bit different. We just see the formula f of n. It means if I plug in a number of x, or n in this case, what do I get for the y value? So find term 8, it says in this example. So we write f of 8. That's my x value, or n value in this case. Substitute n equals 8, 5 minus 16, which equals negative 11. Doing the same thing here, f of 8, 2 times 8 squared minus 1, 127. Okay, so these are that's the 8th term in the sequence. So these sequences can mean a lot of different things. We'll generally see them in terms of evolving any type of mathematical sequence or any type of geometric sequence. We also see something that's called a general form for the arithmetic sequences. So here's our general form where we have t of n equals t1. Well, that's the first term. Here, your d value is the difference between terms. So for these sequences, we'll see that they have a constant difference overall. But the key thing you want to do is you want to look for patterns. So when you're trying, I'll move that p to the next line, trying to come up with different types of patterns that you see in different types of arithmetic sequences, it's this pattern between different numbers that'll help us to determine the difference factor between the two. Okay. T1 we said is our first term, n is the term number, and d is the common difference. So here's our first example, which will help us learn this. Find the formula for the nth term that determines the sequence of 4, 7, 10, 13. Well, if I look at the difference, I can see that I'm adding 3 every single time, okay? Which means that's going to be my d value. So the first thing I see is that 3 matters. T of n, for a second I'm just going to write this as t1 plus my difference formula and minus 1. So that's our general term. My difference I can see is 3 and minus 1. And my first term is 4. 4 plus 3 and minus 1. And I'm going to simplify a little bit. 4 plus 3 and minus 3, which is really, 3n plus 1. So this is my final term sequence for that number. I see the question, find the terms T35 and T50, which is a little bit different for these terms. All I'm doing is substituting in the numbers. So I take my general formula and I substitute 35 to give me 106. And I substitute 50 in to get 151. So I know that this is my 35th term in the sequence, and this is my 50th term. A lot of things we see in natural occurrence, we see acorn shapes, we see, what else can I write? Any type of floral patterning that we see, as well as a lot of other non-organic components. We're going to go on to our second component of series, which is called a recursive formula. All this is backwards thinking. Instead of thinking about the term ahead, think about the term backwards. So, for example, we take this term 4, 7, 10, and 13, and we can write it in the following manner. If I think of the first term of being 4, I can compare all terms to be tn minus 1 plus 3. So if we just talk that out for a second, if I take the term 7 and I consider the term before it, the tn minus 1, if I take 4 and add 3 to it, I always get 7. So this is kind of the same as what you saw before, but backwards thinking. When you write the nth term formula in reference to the term before it, that's called a recursive formula. So again, it's a term of a sequence generated from a preceding term, where our T1 is our starting point and our Tn is our general formula. Make that look more like an N and less like an alien notation. So here's our first example for recursive formulas. Write the first 5 terms of the sequence in the the recursive formula. So you'll see here it says the first term is 11. Automatically I know that's good, and this gives me my general formula. So first 5 terms, obviously I have the first term. I'm going to look at the second term. T2 is equal to T1 minus 4. 11 minus 4, which gives me 7. If I look at term 3, it's term 2 minus 1. Again, because of this, it's the n minus 1. I'll make that a little smaller. The term that came before it. So the term that came before it is 7 minus 1. And we fill out the last one. T4 is T3 minus 4. Oh, I have minus 4 here, which makes this value a 3. And then here, 3 minus 4 is negative 1. So therefore, I get the recursive formula of 11, 7, 3, negative 1. Last example that we'll see before you end off with a class without me. To write this recursive formula, it's important that you have a few different terms. You need to have define the starting 3 terms and then write the recursive formula. So this is kind of a good generalization. Create a recursive formula for the following terms: 1, 1, 2, 3, 5. Okay, so first thing I write out the first term is 1, and I write out the first term is second term is 1. So this is my starting point. From then, I look for patterns. Remember, that's the key. Look for patterns. If I look at the third term here, 2, well, that really equals term 1 plus term 2, right? 1 plus 1 equals 2. So if I look at term n, I get, well, n minus 1 plus n minus 2, because this is really the first term, that's 1 term back, plus 2 terms back. And that's the same here. 1 term back plus 2 terms back equals the third term. So this is my general formula. Note this is kind of new notation for us, so this will take a little bit of adjustment and a little bit of practice in this area. What I'd like you to do is to start to attempt the assigned homework. So these first parts here are on our intro, and the second parts are on recursive formulas. It's important that you try out the kind of standard formulas before you try out recursive. And we will see you on Tuesday. And if you have any questions, you just let us know. Okay, thank you. Bye.